Good day, ladies and gentlemen. It's an honor for me to present to you guys today a paper on accelerated electron detection using CMOS SPADs, or Single Photon Avalanche Diodes. Sorry, I've already said that. My name is Anthony Bulling. I'm in the School of Engineering at the University of Edinburgh. Cool. So in terms of presentation outline, first talk about SPADs, Single Photon Avalanche Diodes, for those who don't know. Then talk about current silicon particle detectors. Then the experiment we did, Scanning Electron Microscope. Then the SPAD imager that we actually used. And then a little talk on what happens with particles when they interact with matter. And then on the results with regards to electron detection. So what are single photon avalanche diodes? Just as the name implies, it's a diode, a solid state photodetector integrated within a monolithic silicon substrate with essentially it's a PN junction with an exposed surface area optimized for single electron detection, single photon detection. And it's designed in such a way that you can bias it beyond its breakdown voltage, what is referred to as Geiger mode. And with that, it inherently has quite a large gain, allows for picosecond timings, it has high sensitivity, single photons, very small pixel sizes, and designed all within standard CMOS processes, and commercially available. Now, applications that are pushing this technology include LiDAR for autonomous vehicles, time-of-flight proximity sensors like in phones, 3D imaging, and biomedical imaging. All of these applications are photon specific, but the mechanism behind avalanche diodes, SPADs, is impact ionization. So when a photon hits the region, it causes an avalanche effect, and we can pass its energy on, and we can detect that through, as you look in the diagram, the counts per second as it passes through the inverter. So a very simple circuit. So we hypothesized, well, why can't this be used into different areas such as charged particles? Because just much like a charged particle, it will hit with matter, it will pass energy, it will cause an event, so surely we should see something. And this opens up all sorts of medical applications, such in medical or tabletop particle accelerators, things like that. But it utilizes all the advantages that SPADs can provide, such as size, timing, sensitivity, etc. And so we look first at what is currently out there. So in this case, current silicon-based particle detectors. So the example of picture is the Atlas Detector Large Hadron Collider experiment in CERN in Geneva. And this pixel, so if you look at this Atlas detector, it is a huge 7,000 ton, 22 by 44 meter detector. It is like, but right at the heart of it, the inner detector is a silicon hybrid sensor. Now, this has been specially made for high energy charge physics, extreme radiation hardness, but the entire process and how the detector works is very much on charge collection. So as charged particles pass through, they give off some electron hole pairs, and that charge is detected. But with regards to fabricating these devices, they are very expensive, very large material costs. It's a labored and costly bump bonding process. They have very large pixel size if you compare them to SPADs, low gain for noise reasons, and then also large bias voltage because of the large depletion depths required. So, this was for very specialized, but SPADs can be used for different applications. And so, is SPADs a potential application for other applications for lower energy, such as scanning electron microscopes. And so we decided to investigate the use of SPADs for charge detection. So we chose a scanning electron microscope, basically to take the SPAD, place it within this same chamber. It's a vacuum, so very little interaction or scattering of the electrons. There's no light in there, so that's good. And basically just irradiate it and see if electron detection is possible. So in this case, we use the Tescan Vega 3 XMU SEM. It allows for micron beam resolution, so we can microfocus the electron beam. It has variable accelerating energies up to 30 keV, so it's not very high energies. Large chamber size, so if you need to put all the electronics and periphery inside, that's possible. And then also it raster scans, so it goes from left to right. Anyway, so when we do the experiment, we should see that raster pattern in the experiment. The image sensor itself is a 3D stack backside illuminated SPAD within a dedicated CMOS process. It's wafer to wafer bonded, face to face, and consists of 120 by 128 pixel array so just over 15,000 pixels. Has a very small pitch size of 7.83 microns, and at 1 volt above the breakdown voltage, it has very low count rate. So it's very good for noise, just to make sure we see the signal. Just to note, if you look at the structure on the left in terms of how it's designed, backside illuminated, so we know that the medium is in substrate, so that means it must be silicon, and so we know the incident material, and also that's been wafer etched down to a couple of microns, just to optimize the path for, in this case, was photons, but in our case, it's very good for electrons. So before we go on to actually showing the results and stuff, we need to understand what happens with accelerated particles as they pass through matter. So I'm sure all of you know this formula, but it's called the Vita-Block formula. It describes the mean rate of energy loss or stopping power. And basically, when charged particles pass through matter, they slowly release energy, or they give energy to the neighboring electrons and atoms, and that energy slowly loses, and then it will have a total stopping power. Now, because we're working at very low energies, electrons don't quite lose energy only in forms of ionization. There are all sorts of secondary effects, such as secondary electrons, backscatter electrons, also causes Bremsstrahlung X-rays, and there's inelastic and elastic scattering effects and stuff. So this is also something we need to take into account when we're doing experiments and stuff. So we can obviously observe to see what that does. So just in terms of the linear stopping power, so using the Vita-Block formula, or there are already available tables online and stuff for different materials and different energy levels. So we know that the back side of the SPAD is wafer edged down to about 5 micron. And so we can see that in terms of the proxy linear step, we should expect to see detection that energy is greater than 20 keV. So that's our first target, so we wanted to see that. So we had to break this up into 2 different experiments. So the first experiment is what we call complete CMOS SPAD exposure. So basically we make the focus of the Scanning Electron Microscope about the size of the SPAD itself, and then just expose it. So we chose an exposure time of 1 millisecond that allowed for us to actually detect the raster scan as it comes across this actual array. We did 100 frames just for an average, and then we just ramped up the electron energies from 5 to 30 kilo electron volts. With regards to exposure area, again, SPAD, CMOS SPAD image sensor, the size of it, I've highlighted this because it's different to the second experiment. And basically, do we observe electron detection, and will we see the raster scan pattern? And then the second experiment is single pixel exposure, so same initial parameters, but this time we microfocusing the electron beam onto a single pixel. The beam area was 0.2 micron, which is much smaller than the actual the diameter of the actual array. And basically, we wanted to observe what the surrounding pixel activity is as a function of those radiative processes that we expect. So, first experiment, and as you can see, we were able to detect electrons, which is great, and as expected, we were able to see electron energies or detection at greater than 20 keV. We weren't able to see anything lower than that. Very little radiative processing as a result of secondary effects, and you can clearly see as it's exposed, or the exposure time for 1 millisecond, you can actually see the raster scanning across those pixels. We had to adjust it to an acute angle to make sure that it is what we are seeing, basically knowing that distance, we can also work out the speed of the raster scan. So that's very cool. And then in terms of if you look at the counts, I don't know if it's very clear. Sorry. So that's about 900. That's about 700. And so there's definitely a correlation with regards to beam energy and incident beam energy, the beam energy and the amount of counts. There's definitely a correlation between the two. And so the next experiment was the microfocus. And what was very interesting here is that we were able to detect electron energies as low as 5 keV. It's much longer exposure time, 100 frames times 1 millisecond, so quite a long time, exposure time. But you can see from increased energies, there's also an increase in surrounding pixel activity. And also, again, it's clearer here, you can see that there's also direct correlation between the counts versus the actual beam energy. And so we plotted that, and it gives a somewhat linear curve, which is very interesting. And so basically, to conclude, we were able to detect electrons using SPADs as a function of avalanches. So what next? So the next step is we've got a collaboration with a group at CERN, the Atlas Detector group. Basically, it's to do further experimentation to determine what is the radiation hardness of these devices. Sorry, one thing to note, when we did these exposures, we did control before and control after, just in terms of the dead count. What happens, the pixels, dark count rate shift, was there any change in how they functioned? And we found absolutely no correlation. It's still exactly, or there was no statistical discrepancies there. It seemed to operate exactly as it did before and after exposure. So we'd like to do some radiation hardening, furthermore some X-ray detection, possibility for medical imaging devices, access to their SPS, which is a pion beam, so move away from electrons, so do something else, and then also access to the ELSA electron accelerator, which allows for ramping up of the electron energies, and also radiation size, as well as the amount of electrons that we can deliver at any time. So a lot of nice parameters there to determine the efficiency of the device in terms of charge detection. And basically, we'd like to demonstrate CMOS SPADs for charge particle detection in medical applications, etc. I'd just like to acknowledge some of my colleagues, Tarek and Robert Henson, for providing access to the 3-step illuminated SPAD and their valuable advice, and then to Tom Davison, Peter Lomax, and Andy Bunting for their valuable expertise. And just want to thank the Commonwealth Scholarship Commission for funding my studies in the UK. Thank you.